Good morning, everyone. I'd like to welcome you to this last day of the conference. Our plenary session today will have two talks. First by Márió Szegedy and then by Fedor Jelezko. For both talks we have scheduled 45 minutes. That's the talk together with the question time. And we will start with Márió. So Márió Szegedy is a Hungarian-American computer scientist, professor of computer science at Rutgers University. He asked me to skip most of his CV, but I am allowed to mention that he was awarded the Gödel Prize twice, in 2001 and 2005, for his work on probabilistically checkable proofs and the space complexity of approximating the frequency moments in streamed data, which doesn't sound very quantum, but I know Márió Szegedy from the so-called Szegedy quantum walk. I used to work on quantum walks, and this became a famous generalization of a quantum walk useful for various algorithms. So with that, I would like to give the microphone to Márió. Thank you.
Well, thank you, János, and I am really honored to be here. There are so many famous Hungarians in the last 200 years worked and gave lectures, like for instance, Ötvös and in a new generation, Laci Lovász. This talk naturally will not measure up to these extraordinary accomplishments, but this is just like our new research that's not even written down. It's just with a group of researchers, we are trying to understand certain aspects of the QAOA algorithm. Actually, this group includes all the authors, or many of the authors of QAOA. Let me just introduce you to the topic. First, I would like to introduce you to the max cut problem, and I apologize for those because what I actually like in this topic is that it's like an intersection of mathematics, physics, and computer science. So in each respective area, like those who know these things will find very easy, but I need to go through all the definitions. So the max cut comes from computer science. It's a computational problem, and your input is a weighted graph. So there are edge weights on every edge, and you can even think of the complete graph, because if an edge is not there, then you just give zero weight to it. So a cut is just coloring the nodes of the graph with two colors, like let's say red and blue, and you just sum up the weights of all the edges that go between the red, so which has two endpoints like red and blue, and the red edges you don't add up, and the blue edges you don't add up, and so this is the value of that particular fixed cut. And what you are looking for, and so that's the task, is to find the cut for which this value is maximized. And so you can actually arithmetize this problem, and in the following way, that so now instead of like looking for the optimal red-blue cut, now every node has an associated number, either +1 or -1, and there is a quadratic formula which involves the product along of these variables. So the associated number for node u is xu, and then you just add up like a quadratic you have a quadratic form which involves these variables. And that's simply that clearly the cut value can be expressed as such quadratic form. I mean, it's just pictorially, and that's what I was talking about, the grouping of nodes into red and blue, so that's a cut, and then you see the cut edges, which are supposed to be purple edges in this example. But what actually makes it fascinating, I mean, this whole topic, is that when you ask a physicist, like a physicist says that, oh, I know this problem, because like I have like a condensed matter, like a material, and like each site is, let's say, an atom where there is an electron sitting, and so the electron is either spin up or spin down, and then there is an energy associated with the spin configuration, which is also a quadratic form, and then nature tries to minimize this energy. So nature actually solves max cut in a sense. So physicists used to work from computer sciences separately on this problem, and they developed like very interesting ideas, and computer scientists have developed other interesting ideas. And for me, the most interesting is when the two communities meet, and actually in this talk I will show you like what this meeting, so a certain problem where like we try to put together all this wisdom, but we are still looking for the solution. So now this so far, okay, maybe I should go back to, I'm sorry, I go back to the previous slide. So when we say spin up and spin down, and we define this energy function, now that looks completely classical. So where is the quantum? So the quantum is when, of course, like we have this like 2 to the n possible spin configurations, and the nature gives you some superposition of this spin configuration. So actually, this quantum superposition of spin configurations also gives you an energy. And so here I define now this energy. So that's a well-known way how you compute energy in physics. So it's like the bra, and then you have the energy operator C, and then the ket of phi. So phi is your quantum state. And so if you measure phi, like let's say you have a quantum state which achieves a certain energy, and then you measure that state in the eigenbasis of, and okay, so that h hat is supposed to be C, because originally it was h and it changed everything to C. So, so you measure in the eigenbasis of C, then you get a classical state, just a single spin configuration, which with a certain energy, and these energies are actually averaging out to the energy of your quantum state. So in short, if you achieve a certain energy with a quantum state, and you measure that quantum state, then you get a classical state which typically has the same energy. So, I mean on average, so on expectation. So, well, that's only if you measure it in the eigenbasis of the Hamiltonian, but in our case, this energy operator is a huge 2 to the n by 2 to the n diagonal matrix, and which is defined just to exercise my laser powers. So it's like here. So that's the energy operator corresponding to that energy function I have just talked about. Okay, so now here comes the interesting thing, because okay, so now the two communities meet, and they say, okay, so we have this problem and you have that, but actually, and the problem is the same, but what is a huge difference is the type of instances the computer scientists are looking at and the physicists are looking at. Because we computer scientists are looking at worst case instances, and physicists are looking at average case instances. There is also an intersection of the two types of instances, well, typically sparse and large girth graphs, but what the computer scientists notice that this is actually an NP-hard problem, the Max-Cut problem, which is like unsolvable. And what physicists noticed is that nature actually solves the Max-Cut problem, so it is not hard. So it seems like a contradiction, but it's not really a contradiction, because when there is an intriguing instance, like for instance, like a protein or some big structure, the nature might just not solve the exact optimization problem. So the same no-go will happen in the nature as what the computer scientists have observed. Moreover, like with these average case instances, like even when the physicists say that yes, we have solved the problem, but they solved it for average case, and the computer scientists say yes, but these average cases, these average instances are not when you design like a, I don't know, for a company, they give you an instance that's not like a typical instance and you still cannot solve it. So also in physics, well, how nature solves these annealing, quantum annealing, and okay, so QAOA, I should have put it in the intersection of physics and CS. And so in CS, we have simulated annealing, so everything is simulated and not exact simulation, but sort of a mock simulation of these. And then, but we also have like linear programming and semi-definite programming solutions. Okay, so now it's for computer scientists, so that's another difference, by the way, that so physicists often think in terms of Ansätze. So an Ansatz is an assumption, basically. It's a clever assumption that the solution of your instance is in a particular form. And physicists are very like resourceful when it comes to guessing the form of the solution, which is actually very interesting to us because at least for the average case instances, computer scientists have never thought of the particular assumptions of the form that physicists thought about. And and there were huge breakthroughs about random instances, not just max cut, but very close relatives, like max reset, and so all those constraint satisfaction problems. Okay, so but this talk, and so this is a huge topic, so but now I highlight 3 landmark results, just to put you into picture. So when we say, okay, max cut is NP hard, so we cannot find the best cut, but we can find a pretty good cut which approximates, whose value approximates the best cut. And so the best such algorithm, and in a sense it cannot be improved, is the so-called Goemans-Williamson algorithm. Now another important highlight, and of course that's the basis of our current research, is the so-called QAOA algorithm, which is a quantum classical algorithm. And I will talk about all these 3 in more details, by Fari, Goldstone, and Gutmann. The third ingredient is, so now let's go back to, let's now focus on random instances. So the QAOA, by the way, these people are physicists, but the QAOA is like an approach with which you can treat any instance. Well, the question is how well, of course, but so now the Parisi theory, and actually Parisi got the Nobel Prize for his observations, not just for this, but altogether. And so he can determine the value of the max cut for certain type of large random instances. And actually it's a very complicated theory, and so it's really remarkable that he just created that out of nowhere, and he just solved the random instances. Let's now go into more details. So how the Goemans-Williamson algorithm, the idea is that, and that's not their idea alone, that so when you have a problem, you can look at the semi-definite programming relaxation. They just apply that relaxation to max cut. And so the way how you relax like a problem, like if you have a quadratic form, like our objective function, then you just, and which involves numbers like xu and xv and so all the xi's, then you just replace these numbers with vectors. And so you replace the product with the inner product. So of course it works only when it's a quadratic form. But when you do that, then you can evaluate the same formula for vectors. And the interesting thing is that now you can maximize in polynomial time. So if these are numbers, you cannot, but if these are vectors, then, well, you are maximizing over a larger domain, which means that the new maximum will be larger than the original maximum. However, now comes the interesting thing, that you can actually, from the vector solution, with a certain compromise, you can get back a number solution. And so the compromise is a factor which is 0.878. And so if you find a vector solution, the optimum vector solution is better than the optimum number solution. But when you do the compromise, then you lose a factor of 0.878. And so that's gonna be the approximation factor of your algorithm. So the other component, the QAOA, is actually an AI-inspired algorithm by Farhi, Goldstone, and Gutmann. And so here the idea, and that's why I talked about ansatz, because I just define a quantum state which is created from the instance in some clever way, and there are parameters to optimize. These are the beta k and gamma k. So now instead of optimizing over the xi, so somehow with a clever twist, now I need to optimize with some other over some other parameters, and it's not just a rewriting of the original formula, but it's an ansatz. So there is a brave assumption there that you are looking for the solution, and first the quantum solution, and then you measure that quantum solution, and you get a classical solution in the end. So whatever this formula is, then you have to find those gamma beta parameters, and so the way how you find, and that's where the AI comes in, that you find them in a feedback loop, sort of. You just start from some gamma and beta, and you can do like gradient descent or whatever, and in the end you get a better, and I mean hopefully the optimum solution. And actually the authors like proved, like Farigonson and Gutmann proved, that in fact if, okay, so just again I apologize, just go back to this formula. So it has this P. So what is the P? Well, the P is, so this is actually, this formula represents a quantum circuit which is originally fed in some state that it's easy to produce, like plus this, the plus state to the end. So every bit you put in the plus state, and then you keep applying operators, like unitary operators. So this e to the minus I gamma k c and e to the beta k b are unitary operators. And these are layers of your quantum circuit. So the more, and so how many layers do you have? You have p layers. And of course, the more complicated your ansatz is, on one hand, that makes your life more complicated. On the other hand, that ansatz has like more chance of being, of working and getting closer to your maximum. So actually, if P is very, very large, then your ansatz has a lot of parameters. On the other hand, on the other hand, the FGG have proven that in that case, there is a gamma beta there are gamma beta sequences that reach the optimum. And so actually it's not very hard to prove, because like all physicists know the adiabatic theorem, and this is just noticing that adiabatic theorem type of idea, and actually basically just the adiabatic theorem itself almost, is just applicable here. So now the Parisi theory, which is maybe the most obscure to computer scientists. So in the Parisi theory, again, so what is the random instance? Because when we say random instance, it can be like you can define like and I will talk about like defining random instances differently, but the way how we define here is that a complete graph where every edge weight is randomly chosen from like the standard Gaussian. So, but I could have chosen actually from any distribution, the same or maybe even not the same distribution for every edge, but maybe you need the same distribution, where the distribution has the property that it has 0 expectation and variance 1. But so for this talk, let's just, except in the very end, let's just stick to the standard Gaussian. So that's your instance. So far I defined like an assembly of random instances. And so if you have such an instance and your instance is very large, then the max cut is basically it's gonna be very close to, and okay, so it's not the max cut because so physicists minimize the energy, so it's going to be minus 0.763166 n times square root of n, and so the n times square root of n is the order of magnitude, and I will tell you why it's n times square root of n. So this theory involves replica symmetry breaking and order parameter. So these are concepts that go beyond this work, but I should mention that Parisi himself could not give a full mathematical proof, and very serious mathematicians like Talleyrand and Panchenko eventually proved that rigorously. So why the ground energy is like, and so forget about the Parisi constant now, so why is this n times square root of n the right order of magnitude? Well, think about that you are trying to find the maximum solution, and you are going like spin by spin, and to each spin you want to give either a +1 or a -1. So when you go to the next spin, so already the previous spins are determined, then you have like a sum like this. What did I do? My God, that's okay, like this. So you have a sum, and so this sum, you can think of the WJNs. Okay, so these are random Gaussians, but you can think of like random +1 and -1. And so the XJs, so these are the XJs, are also previously determined. They are just either flip the phase, we just either flip the sign of WJNs or not. So it's like a random sum of like n-1 numbers, and each are either +1 or -1. So this is theta square root of n. So, and then when you determine the new spin, you can always just determine it to be +1 or -1, that order of square root of n number actually adds to your energy, or actually in the physics case it subtracts when you minimize the. So that's why it's n square root of n. And it's easy to prove by very super simple probability theory that it's not bigger than n square root of n. So that's the right magnitude. Now, I want to say that there are other types of random instances can be defined, like a random graph, like you either put an edge there with probability 0.5 or you don't. And if you And for these instances, it's a completely uninteresting, because you know that it's simply 1/4 of n squared. So then so the difference is that in the former case, every number is positive, and it has a non-zero expectation, and then it's just the expectation method. So the Parisi instances, however, show this complex behavior, because so it's the plus ones and minus ones, or plus numbers and minus numbers cancel each other, and so what you are trying to cut, you are trying to determine is really how did I put it, is the random fluctuation in this model, and that's why it has a very different mathematical behavior. By the way, at the IBM, when I visited there, they said, oh, here we have our quantum computer, and here is a random graph. And our quantum computer is gonna compute the cut of this random graph. So that was the first instance, first type of instance. And it was a random graph of a graph with 10 nodes. And they said, okay, so can you guess what is that? I said, yes, 10 times 10 is 100, and 1/4 of 100 is 25. So sure enough, then they put the quantum computer, the genius computer, and it gave out 24. so it's no brainer for random graphs to compute the max cut. Okay, so now we connect things. So how do QAOA perform on the Parisi instances? And so here, the funny thing is that so we know that if we fix an instance and we go with P, so this QAOA circuit to infinity, and we optimize the parameters of the QAOA circuit, then we can reach the energy, the max cut value of that fixed instance. But what happens if we first fix P and then we increase the size of the instance, still keep this Parisi instance? So we are talking now about these intriguing Parisi instances. So we take larger and larger, but we fix the depths, and then we can, and then for every depth we can get a pretty good cut, which is going to be of order n, the square root of n, so the order is going to be right with a certain coefficient, and again, depending on p. And so if everything is true, then these values, so these optimum values, so this is just one number for every p, and so I call them nu1 for p equals 1, nu2 for e equals 2, or nu2 bar, and so forth. So if everything is good, then these numbers just should tend to the Parisi value. However, the Farey-Goldson-Gutman theorem does not apply, because for a fixed p, these are increasingly larger instances, as opposed to having a fixed instance and taking increasingly large p. So it's sort of like, you know, there's a two-way stable, and if you look at the limit this way and then this way, and then if you look at it in the other way, then it's not proven that the two ways of taking the limit is the same. So that's the huge issue, and so our huge issue that we have been investigating for several months by now is that, so do these numbers tend to the Parisi value. And actually they look, but, you know, who knows? But why we study these things is because if I take a fixed p, so in this case, I don't know, p equals 4 or something like that, then in this particular, again, I'm just, so in this particular instance, then we can compute this new p for, okay, so this table is constructed not for the optimum gamma beta, but for any gamma beta. We have such a table, and so for fixed gamma beta, we can construct this matrix, and from this, and from these numbers, then, okay, so this is how we construct in a pretty complicated way, and from the numbers in the matrix, then we construct this new bar for that particular p, in this case p equals 4. But, so then now there are tons of tasks, because first of all, this formula is complicated, and secondly, we don't even know how to optimize the betas and gammas. So let me expand on these just a little bit. So actually, that's just sort of my fantasies that since it involves some complicated exponential sums that we have never seen before, I propose that we introduce calculus, which deals with such sums, and so all integrals and whatever are computing these kinds of formulas. But that's really just science fiction. So I like science fiction, so what the hell, I just told it to you. But so more seriously, like also there are intriguing questions about how to optimize beta and gamma, because it turns out, so experiments show that there are these intriguing limiting terms for the optimum beta and gamma, and we try to understand the shapes of these limiting curves, but the most intriguing about it is that the Farry-Goldstone-Gutman basic theorem would say that all betas and all gamma, when we fix the instance, and again, their theorem says that then we can reach the optimum, but these are all small betas and gammas. And so in the limiting curves are these betas and gammas involve constantly large numbers. So why are they good? And so there is another kind of adiabatic theorem, which is called discrete adiabatic theorem, which is about, so the original adiabatic theorem is about a changing Hamiltonian. And so now we are, instead of having a changing Hamiltonian, we have these unitary operators that we keep applying on a state, so the state jumps, like it makes huge jumps, because these unitary operators are not infinitesimal unitary operators. And so, but we can modify a certain very nice proof of the original adiabatic theorem, which was developed by computer scientists for and Ambainis and Regev, to show that this discrete adiabatic theorem actually holds, but still it's not enough in our case. So my last slide is that refers to this this sparse, very sparse instances, so deregular graphs. So what the hell do deregular graphs have to do with the Parisi instances? And notice that when the D is large and it's like a random deregular graph, then in fact it's a Parisi instance in disguise, in a sense. Because if you take a random variable which has very small, d is very small compared to n, because n goes to infinity and d is constant. But if you do that, if you put an edge into your graph, I mean, you have to appropriately linearly transform. But so there is this very tweaked probability distribution, which actually sort of gives, so now every edge you pick according to this, then it gives you large deregular graphs. And so actually all the arguments of Parisi applies in that case. So that's how we do that. Now, at this point, let me stop, and I apologize. I thought I had more time, but time for questions.
Thank you for the really nice talk. I have questions on the spectral gap. When you use the adiabatic process to solve such the max cut, you can see an exponential close of the gap with the system size. I just want to ask, how do you overcome this if you use QAOA?
So I'm not sure I completely heard the question. So you are talking about gap?
Yeah.
Mm-hmm. Yeah, so, well, so are you talking about the Parisi instances or the QAOA in general, like for just any instance?
Yeah, because if the gap close, which means you use adiabatic process, you need exponential time because you need to, around the close of the gap, you need to move very slowly. Mm-hmm.
But okay, so I think I get you. So if you go back to this discrete adiabatic theorem, so we are not fully satisfied with that, because I wanted to put here another sentence, but I did not, so the gap is exponentially small typically, and so we cannot apply this, so it's not satisfactory, but we want to find a low energy, so not necessarily the optimum solution, but a low energy solution. So there should be a further development on this theorem which addresses your problem, which finds a low energy solution. And so it should be enough if the low energy is separated from the large energy, yes.
Okay, thank you very much.
Thank you. In the interest of time, I suggest that you find Márió Szegedy in the coffee break with further questions. And we should continue. Let's thank Márió again.
Thank you.
I ask Ádám Gali to introduce Fedor Jelezko.
Okay, Professor Fedor Jelezko, he is the director of the Quantum Optics Institute at Ulm University. And he was born in Minsk, but later on he worked in France for a PhD, and then later he continued to work with Professor Jörg Rackstrup at Stuttgart University, when he has become later, as I told you, the director and a professor at Ulm University. And I believe he is the kind of main engine I told once, but I still, the main engine of this Diamond MV Center research. And he was one of the founder of this field for this type of quantum technology, in particular for quantum sensing, and he is working on biosensing, using this technology for biosensing and other related tasks. And we are very happy that he can show his latest results and an overview on the field. Thank you very much.
Thank you very much, Adam, for this introduction. Also, I would like to thank organizers for this exciting event and celebration. 200 years of academy and 100 years of quantum is, of course, a very strong coincidence in time. And today I'm very happy to present our results on spin qubits and diamond. It will be about experimental progress towards building a quantum computer, a quantum repeater, based on solid-state defects. And so we have a session here on defects and atoms. And if I compare atoms and defects in solid, or in general solid-state systems with atomic systems, usually they're quite different. Solid-state systems are more scalable. They can make devices more compact. But on the other hand, often they suffer from poorly understood environment, decoherence. They act differently. You often need to select the very best solid-state qubits compared to atoms, which are all the same. But defects in solids, localized states of electron spins, which are optically active, are somehow similar to atoms. In this sense, color centers, defects in solids-based qubits are maybe very similar to atomic system. And we are going to talk today about this. Maybe in general why you can use color centers as a qubit and what are criteria for a solid-state system to be able to host good color centers. I put here some notes. So for this solid-state material, the host need to have a wide band gap, because within this band gap you can put localized states which can be connected by optical transition, which you can read out. Ideally, the host should be capable to offer nuclear spin-free lattice to avoid your qubit to interact with very dense nuclear spin bus, allowing long coherence time. And also, from practical point of view, you need to have a technology to be able to grow very, very pure crystals, where you can place these qubits one by one and there is no parasitic impurities. And there are several systems which are now under development. It's silicon carbide, very interesting material in terms of technology. You can grow large wafers, and both silicon and carbon offer spin-free isotopes. Yttrium silicate with rare earth dopants also came into this play of development of qubits. There is a variety of two-dimensional materials which are explored, but diamond is also very known by hosting color centers having a wide band gap, and most abundant isotope of carbon is nuclear spin-free. There are more than 500 known color centers, and several of them have been explored during last decade as a qubit, as an element of quantum register, enabling sensing, but also computing and simulation and communication. The most known, perhaps, at least in terms of quantum technology application, color center is nitrogen vacancy. So if it's, you replace carbon in diamond lattice by nitrogen and have a vacancy nearby, this forms a 6-electron system having a strong optical absorption, leading to coloration of diamond when present in high concentration. The energy level of these color centers are interesting in terms of quantum technology applications, because the ground state of this color center is a spin triplet, and it's connected to excited state triplet by a strong optical transition. The ground state triplet allows you to use spin sublevels as a qubit, and optical excitation and spin selective relaxation towards singlet and back to one of the sublevel of the triplet allow you to initialize and read out the spin state optically. So just by exciting your color center with lasers, you can initialize one of the spin state. And in addition, because the transition to the singlet state is spin selective, you also get different optical response. Fluorescence intensity is now then, owing to this shelving, spin dependent, and if you measure fluorescence as a function of time after you shine your laser on the color center, you will see the difference between MS equals 0 state, which is brighter, and MS equal 1 state. And so this difference can be used for measuring, accessing the spin state, and this is very sensitive technique. Fluorescence microscopy can detect even single molecule, single qubits, and so that's allow you to access the spin state optically very efficiently. I need to say that usually we don't collect all the photons, and experimental apparatus is lossy, and we typically need about 100 times to repeat the experiment before we get enough signal to noise ratio to detect a single spin with high enough signal to noise. The experiment typically is a combination of magnetic resonance and fluorescence microscopy. We excite color centers with microscope objective. We collect fluorescence using the same objective lens, detect photons with high efficiency. I mentioned before, in a way, we lose part of photons, but those which are reaching avalanche photodiodes are detected with close to 100% efficiency. And we add usually antenna to excite spin transition, and once your microwaves are resonant with your ground state spin sublevels, you get a response in fluorescence. Usually there is a drop by 30% in fluorescence intensity for this color center, allowing you to access the spin state. You can also do coherent control. Once you found the resonance of color center, you can apply microwave pulses and excite oscillation of spins, coherent oscillations. Here you see the example of Rabi flops. We can control the spins on a nanosecond time scale, and the coherence time of the electron spin of NV center, even under ambient condition, can reach a few hundredths of microseconds. And this is important resource. This ratio between ability of the drive speed and the coherence rate is something that is very important as a benchmark for qubits. So here you have close to gigahertz drive and kilohertz dissipation in the system. So let's give you already an idea that this can be an interesting qubit. I mentioned it before that typically we are not really doing Q&D measurements, so we are not measuring in a single shot. We need to repeat measurement many times, and that can be a drawback for some applications. For example, measuring quantum correlations, violating Bell inequality, or establishing entanglement over distances based on projective measurements would suffer from inability to measure spin in a single-shot Q&D manner. But for NV centers, there is additional tool to do this, is to use a nuclear spin. There is a second qubit always present in a structure of NV center. It's a nitrogen nuclear spin, and this spin qubit has very long relaxation time. Even when you measure electron spin, it keeps its projection, and this can be used for a repetitive Q&D type measurements. How it works, so here you see the fine structure, or hyperfine structure of one of the spin transitions having 3 separate frequencies corresponding to different nuclear spin states, and so you can apply a pi pulse of microwave mapping the state of the nuclear spin on the electron spin. So if you apply a selective pi pulse here, so you will flip the electron spin only for one particular nuclear spin state, and after this you can measure the electron spin state, and you can repeat this process many times, and during this repetition the projection of nuclear spin is not perturbed, so it allows you to repeat and gain information about the nuclear spin state even in presence of losses of photons. So how it works, so if you do these pulses and measure fluorescence intensity, remember the electron spin state is dependent on, is affecting the fluorescence. You now will see that fluorescence intensity during this application of the pi pulses all the time, they are applied about 1,000 times per second. It jumps between up and down. This is a real time, and so what in y-axis fluorescence intensity, in x-axis time, and so you see discrete jumps, and those are quantum jumps. So you can observe now nuclear spin live jumping between spin up and spin down. Those are quantum jumps which were a kind of Gedanken experiment in the early stage of quantum science, but now you can observe it in a real time and even in the ambient condition in a solid. So although in the solid state there are many perturbations, but these nuclear spins are very well isolated. And now you can also put a threshold. If you are below certain fluorescence intensity, you are in spin down, and if you are above, you are in a spin up. And taking the threshold, and you will see that there's a photon counting distribution have 2 peaks. So if you put a threshold just between these 2 peaks, you can now discriminate between nuclear spin down and nuclear spin up in a single short QND manner. And this ability to measure quantum system very efficiently without destroying eigenstate is also a very important element. So today I would like to touch now applications of these Scala centers, and I won't have time to discuss all possible applications, but we'll talk about the research towards building a small scale quantum computer or element of quantum register going beyond 1 qubit. We know very well nowadays how to read out and control a single Scala center, but many technologies require control of several tens or even thousands of them, even tens of thousands, and that's current effort in the field, how to go beyond 1 qubit. And we are exploring as a community 2 types of interactions, 2 types of coupling mechanism. One is a dipole-dipole coupling between qubits. You have your NV centers with auxiliary nuclear spins, and NV centers electron spins are interacting magnetically via dipolar coupling. And the second avenue is to use photons. Spins of Scala centers are intrinsically coupled to photons, and so having mapping the state of spin to a state of photon and then let the photon to interfere and the beam splitter allow you to generate entanglement over distant spins. So these 2 avenues are currently pursued. Both have pluses and minuses. Second approach based on photons allow you to build a distributed computer, which can be a quantum computer, which can be very important. In the first case, you might have fast operation rates and a more deterministic gates because you are not relying on detecting of the photons. I will start with this first approach, how to connect NV centers electron spins via dipole-dipole coupling. And so this is a sketch how this register can look like. You have NV centers electron spin qubits which interact. This interaction is not very strong, in fact, interaction between 2 single electron spin. And so you need to control the spin and isolate your spin from unwanted environmental noise very carefully. You need to place your spin close enough that the interaction strength is faster than the coherence, and there are currently several technologies, key technologies that need to be developed in this respect, so you need to be able to develop techniques allowing to address these spins, which will be separated by a few tens of nanometers optically or photoelectrically. You need to develop technology for single ion doping, allowing you to place color centers very close. And also you need to generate diamond, synthesized diamond, which is pure enough that there is no environmental perturbation, allowing you to keep this register under control. Owing to enormous success in material science, nowadays we do have several techniques that allow us to place these color centers one by one on desired position. And for this, you first of all need a diamond that don't have any parasitic color centers. And nowadays, material science groups can synthesize such diamonds. They're even available commercially. And then you can take ion beam and create dopants of nitrogen one by one. After annealing, they can be converted to NV centers. It can be done either with ion beam or just focusing it, or if you want to shape your point better, you can use nano apertures, or do it in a larger scale via e-beam lithography structures. And this approach, you can reach position and accuracy on the order of 10 nanometers. So far, all these approaches have been probabilistic because the ion beam is have a Poissonian noise. So if you want to implant on average one NV center or one nitrogen, you would have some distribution. So you have to work with some noisy number of implanted ions in a spot. Already in the early days, there were proposals how to create color centers deterministically, and the first idea came from Ferdinand Schmidt-Kahler and Jan Mayer. They proposed to use a single ion trap, a small kind of ion trap quantum computer, and place together with calcium ions and nitrogen ion, and then extract these nitrogen ions from the trap and implant it in diamond after accelerating. In this case, predicted position accuracy could be below a nanometer, because it's very well-defined ion source with very well-defined energy, and so there is no aberrations, there is no fluctuations. And more recently, this experiment have been built by Ferdinand Schmidt-Kahler, and here you see first implanted from an ion trap in V centers. At the moment, although we can implant deterministically single nitrogen, we can not yet create NV centers deterministically, because conversion from N to NV is not still 100%. So we don't see this very nice pattern here, but only a few random spots. And this is current effort to make this conversion efficiency high enough to basically convert or transfer deterministic ion implantation to deterministic color center implantation. But position accuracy in this case, because of this very well-defined ion source, is extremely high, expected to be just a nanometer, and then a little bit broadened by a straggle of ion when they penetrate into a diamond lattice. In parallel, in collaboration with Shinobu Onoda and Takeshi Oshima Group and Japanese Institute for Quantum Science and Technology, we have developed an approach where we don't take a single ion, but take a molecule having several nitrogen in its structure. In this case, when the molecule been ionized and penetrates into diamond lattice after acceleration, so it's a molecular implantation, the nitrogens are remaining very close. And in this case, even without focusing ion beam, you can create clusters of nitrogen and clusters of NV centers. Here you see the example of implantation of adenine molecule having 4 nitrogen in its structure. On the right side, you see the implanted area. Now, every spot corresponds to a cluster of NV center. Actually, dark spots correspond to a single NV center because we have a limited conversion efficiency. Even those we implant for nitrogen, we must just get 1 NV center, but some of the spots are twice brighter. So this is in this brightness distribution this peak. And those are corresponding to 2 NV centers, and those NV centers are very close because they are coming from the same molecule. So if you now apply a magnetic field and you look at the resonances you have seen before for a single NV center, you get 2 transitions because it's been triplet. For 2 NV centers, you get 4 transitions, and they're splitted because of different orientations of 2 NV centers. They feel different field along the axis. So, and this splitting allow you now rotate, drive NV centers separately using frequency selection in the microwave domain. And you can now use this coupling and ability to drive and control coherence in a single qubit level to create gates between NV center, flip one of the NV centers conditionally on the other. And this is the very key element of every quantum register, ability to measure a single qubit, ability to control it, but also to create a 2-qubit gate. The dipole-dipole interaction is responsible for this 2-qubit gate. You can understand this principle in a simple picture. If you flip one of the color centers in the Bloch sphere in the equatorial plane, it will start to precess. And precession frequency will now depend on a magnetic field created by a second NV center, which is located close by. So it will precess clockwise for NVB, control NV center in spin up state, and will precess counterclockwise for NVB in a downspin state, and that created different precession rotations. And if you wait for a pi precession angle, you will get an orthogonal state of 2 NV center qubit state, and that basically allow you to make a conditional flip of the spin. The time you need for this is dipolar coupling inverse time, and for our case, it's about 2 microseconds. So we need 2 microseconds to make a gate. Coherence time of these qubits is on the order of a few hundreds of microseconds, so we can do several tens of gates before decoherence happens. You can also visualize this by so-called repetitive benchmarking. When you apply gate many times and you see how the state, ideal state survive, you start with high fidelity, your end state after gate is the same as you expect, and then you start to decay. You should repeat this experiment for all possible input state of the qubit register and take an average to measure the fidelity. And in our case, the fidelity is about 97% here. So decoherence really is responsible for about only 1% of infidelity. The rest is coming from imperfect microwave control crosstalk. So we are working on eliminating this technical noise, and we hope to be able to reach about 99% fidelity plus in the near future. Saying that NV centers can be scaled to a few qubits, so we are still having a long way to go to thousands, and that's strongly rely on ability to implant color center with very high precision. On the other hand, there is another opportunity to scale up this qubit register, is not by using basically very precise implantation of NV center where you need a few nanometers accuracy to make them interact, but rather by using self-assembly of spins in diamond. And this is a work along the early idea that we have proposed with Jianming Cai, Alex Retzka, and Martin Plenio where you have a single NV center located close to an array of nuclear spins in diamond. These nuclear spins can be fluor nuclear spins on the surface or carbon-13 nuclear spins, which are engineered inside of diamond lattice. I mentioned before that diamond is mostly nuclear spin free. That's why coherence time of qubit is so good, but you can also introduce nuclear spin half carbon-13 atoms and make them in a layer interacting, and those nuclear spin can be now used as a qubit, and NV center can be used to cool this nuclear spin and to read out them. It's a bit like an NMR quantum computer. You know that NMR quantum computer was a leading candidate for quantum computing technology in the early day, but somehow it failed because it was not possible to initialize nuclear spins and read them out very efficiently. But here, the NV center provides access for initialization, cooling this nuclear spin register and reading this out. There was also, in the early days of solid-state quantum computing, developed a similar proposal about making silicon-29 quantum computer and silicon-28 by Koei Ito. But so the key element which differs us from this early work is that we use NV center as a cooling and reading out qubit. If you now look on magnetic field created by this nuclear spin above NV center, the NV center will sense the different nuclear spin for ferromagnetic and antiferromagnetic arrangement of this nuclear spin. If you change the interaction strengths between nuclear spins by driving them, you can see the transition between ferromagnetic and antiferromagnetic phases. So in this case, this nuclear spin array can be used as a quantum simulator. So it's not really a universal quantum computer where you gate, but you rather control the interaction in large number of cooled spins, and you watch the phase transition. You can generate collective states. This self-assembly technique is very forgiving in terms of synthesis. Even if you have 40% of holes in your layer, you will still see the signatures of these spin transitions. Now I would like to show you some very first step towards experimental realization. It's an approach which requires a very thin layer of carbon-13 diamond inside of the 12 diamond adjusted to nuclear spin. So we need to create atomically thin layers. We do it by growing diamond in a plasma synthesis apparatus, and then exchanging the gas, which is a carbon source for CVT growth, with basically changing C12 gas to C13 gas and back. That's allow you to create a very thin pancake of carbon-13 diamond inside of the C12 material. In addition, then we implant NV center to place them very close to this carbon-13 layer. We also need to cool the nuclear spin, and usually the electron spin of NV center won't cool nuclear spin because the energy is different. There is a way to do this. If you drive your NV center electron spin with a frequency matching the Larmor frequency of nuclear spin, is called hyperfine matching Hartmann-Hahn resonance. And in this case, electron spin now has the same energy as a nuclear spin, and nuclear spins that can be now cooled using optically cooled NV center electron spin. Here you see how the NV center loses its polarization by transferring it to nuclear spin if you repeat this process many times. On a cooled nuclear spin, you can now apply radio frequency pulses. You can drive this ensemble of nuclear spins on a tens of kilohertz time scale. Interaction between them is just about 2 kilohertz, so you can drive faster than interaction, meaning that you can also tune the interaction between nuclear spins. We can also see the signature of dipole-dipole coupling between nuclear spin. If you now using this approach, cooling nuclear spin, reading nuclear spin within V centers, if you do Ramsey fringes or Hahn echo experiments or Vahucha sequence, different types of coherence measure, we can see that Hahn echo is not doing so good in terms of prolonging coherence time of nuclear spins. They decohere very fast because of dipole-dipole interaction and not anymore this isolated nuclear spin. But if you apply a homonuclear decoupling echo like Vahucha, you see a very significant increase of coherence time by more than order of magnitude, and that's because this echo is canceling dipole-dipole interaction. We can also create a collective state, collective quantum state, by leaving the spin to interact. And one of the manifestations of collective couplings, coherent coupling and creation of this collective state is robustness to drive imperfection. If you apply train of pi pulses, you can observe so-called discrete time crystals where the couplet system, couplet spin system, is very robust against imperfection in flipping the spin. So here you see the evolution of this nuclear spin layer for different tunings of strengths of coupling. And you see if we tune the coupling to be weak for imperfect drive, we see that the system don't really follow periodic pi pulses, so it's kind of decays or haven't beaten. But if you leave the system to interact stronger, then the system perfectly get flipped forth and back. So every time you flip nuclear spin up and down, but you do it not very precise, and so if you leave the system to interact strong enough, the flipping is perfect and not decaying even in presence of imperfection. This phenomena of creation of collective state, which is very robust against imperfection in drive, is called realization of the discrete time crystal. All right, and so now in the last part, I would like to switch a bit the gear and give you an overview of current work on making connections between qubits not based on dipole-dipole interaction between spins, but rather by using optical channels. Entangling spins via photons is a very important avenue of research where many systems are now under investigation, atoms, ions. This is because this coupling of atomic qubits, stationary qubits via photon allow you to realize elements of quantum repeaters, but also models of quantum computers. And color centers are among systems which can be interesting in this respect. What you need for this, you actually you need to have a stationary qubit. That state can be mapped on a photonic state, and then the photon propagate either to detector or to another spin qubits and realize non-local coupling, non-local interaction. That's basically a very important ingredient. But for this, you need to have a tool to be able to map the state of your spin to the state of the photon with a high efficiency. So InvCenter is among the system which is interesting in this respect, despite its drawbacks. What are drawbacks of InvCenter? Well, we mentioned that it's solid state, so it's more complex than atom. For example, in the fluorescence emission spectrum, you observe atomic-like transition, which is called the zero phonon line, which is only 3% of total intensity, and most of the photons are emitted in so-called phonon sideband. It's a photon emission with excitation of phonon in a lattice. Although those photons can be interesting in terms of detecting spin state of NV center, for entangling the spin state with photons are not very useful. Only this atomic-like transition and zero phonon line are really useful in this respect, and only 3%. And so now if you have two of these color centers, only 3% of time the emission works. The second color center having the same problem, and so then so you need to square this number, then the only very small fraction of attempts to create entanglement will be really working. So this is one of the challenges. The second challenge is very high sensitivity of NV center optical transitions to strain or imperfection in the crystals, owing to linear stark shift. Color centers experiencing local gradient of strain will have different frequencies, and now if these two color centers having this shift in absorption will be emitting photons, these photons will have different colors, they won't interfere. So this is the second challenge. And there are efforts to address this by tuning color centers to the same frequency or by enhancing zero phonon lines to coupling to cavity, but they might be also better color centers than NV center for this application. And one of the systems, or family of color centers, are group 4 defects, silicon, germanium, tin, and lead atoms incorporated in diamond lattice, because the size of the dopant, silicon, germanium, tin, and lead, is larger now than size of carbon by a lot. So the dopant cannot replace the carbon in a lattice position, but rather gets shifted to a position between two vacancies to accommodate larger size, and that creates an inversion symmetry, absence of the permanent electric dipole moment, that it means absence of linear first order Stark shift, and that make your centers less influenced by imperfection of diamond lattice, making them more atom-like, having the same fluorescence emission. Here you see the picture of several color centers now mapped inside of diamond lattice, and every single spot corresponds to emission of a single color centers, but the color corresponds to kind of spectral overlap. These color centers are overlapping very fully, so you cannot distinguish photons emitted by them. You can send the photons to the beam splitter, and two color centers, photons will interfere, creating an hongo mandel deep with high visibility. Those color centers are very similar for this family of group 4. They cover all visible spectral range. Currently, we are working in our group more with a germanium vacancy center, which is emitting at 637 nanometer. You also appreciate a strong zero phonon line, atomic-like transition. And so recently, there was also effort to demonstrate that apart from this uniquely homogeneous and stable optical transition, these color centers also have spins. Actually, contrary to NV center, these color centers do have a spin half as a qubit state, also connected to excited state spin half system. But in addition, they also have orbital state. And unfortunately, some dynamics associated with orbital state is decohering the spin state. That's why experiments in this platform need to be done at very low temperature. At least for germanium and silicon vacancy, we typically work in a dilution refrigerator where we can still do the microscopy, but now at milli-Kelvin temperature, we can pump these color centers with light by exciting one of the spin transitions or optical transition connected to the same spin state, and we can see that the system decay in a dark state. We polarize into state which is not resonant with the laser. We can also do this Q&D readout. I mentioned it before in context of NV center. For NV center, we need a nuclear spin as auxiliary observer to do this repetitive readout. For the germanium vacancy center at low temperature, you have enough cycles of photons before the electron spin get flipped that you can do this Q&D readout and observation of quantum jumps and distribution separation of photon counts, even without employing a nuclear spin. You can do it better with nuclear spin, but even without employing a nuclear spin. So you have a readout fidelity in a single shot about 96%. And you can also drive this nuclear spin coherently. So this is another important tool. You can measure coherence time with different approaches. So the very simple conservative approach to measure coherence time with Ramsey fringes or Hannecker show relatively limited coherence time. But if you apply more microwave pulses, decoupling better from the environment like CPMG echo, you can enhance prolonged coherence time up to a few tens of milliseconds. And this is, again, need to be compared with a drive, which is in tens of megahertz. These color centers also have auxiliary nuclear spin, can be silicon-29 or germanium nuclear spin, but even better, carbon nuclear spin. They can be used as a resource, cool it and read out, but also provide more longer coherence time. We can polarize them either by Hartmann-Hans resonance, I mentioned it before, or by using some gates between electron spin and nuclear spin. And so this nuclear spin have been shown to have a very good performance in terms of storing coherence for a long time. Here you see the decay of echo. Now measure it on a single nuclear spin, which is coupled to this germanium vacancy color center. And if you apply a large number of pulses for decoupling, you can reach coherence time up to 3 seconds. So this is now long coherence time if you want to distribute entanglement over distances. Okay, and I mentioned that currently experiments are technologically challenging, often because you need to go to very low temperature, and then the microwave drive is very demanding. In order to avoid heating, we have to keep our microwave power low, but for two members of families of this group 4 defects, tin vacancy and lead vacancy, especially lead vacancy, we expect the operation temperature to be above 4 Kelvin, so making it technologically much more straightforward to implement. All right, so maybe then to summarize, I just highlight again avenues to scale quantum registers and diamond. So it can be optical or magnetic coupling. And both techniques have advantages and disadvantages. Optical coupling allow you to go over distances, allow you to discard qubits that are not working because the system is modular. And the electron spins allow you essentially sometimes faster operation and to be deterministic, not probabilistic. Thank you for your attention.
Thank you. We have time for one question.
Thank you for the very nice talk. I have a very technical question, I guess, so maybe not interesting for many people, but when you were showing the germanium center with the C1, C2 transitions for the hyperfine states, then when you pump either of the transitions and you populate either of the levels, you have to be able to fall back and basically flip spin states. So maybe could you elaborate a bit on what is the responsible mechanism for the spin flipping when you de-excite from the excited state back to the ground state?
Yeah, absolutely.
Because it's electric dipole forbidden, the transition, absolutely, as far as I know. Thank you.
Yeah, exactly. So in a simplified picture, so when you excite one of the transitions, there is excitation without spin flip, so but there is a very weak process of relaxation to another spin state. So I discard at the moment nuclear spin, only electron spin. There is also nuclear spin shown here. And that leads to this shelving into dark state. And so with this you can initialize. So you now pump to the dark state, but now if you take a second laser, for example, and it's shown here on the top actually, and scan the second laser, you will find the system in this dark state get excited back, and this is this detuning of 200 megahertz, which would correspond to this detuning between two spin state transition. So here you use this very weak relaxation to initialize. So there is a kind of forbidden transition relaxation. But you can also initialize actually if you count photons fast enough, so you count faster than this relaxation, then you can see whether you are in a cycling state or not, and you can also initialize by this QND readout. That's another way.
Thank you. Let's thank Fedor and Márió again.